All right, so coming back together again. So remember, last week we started Unit 2, which is all about exponential functions and logarithmic functions. Specifically right now, we're focusing on the exponential side of things. Logarithms we'll do about halfway through. Now, for 2.1, 2.1 is a little bit weird because we got to jump a little bit back and forth a lot. So we only want to focus on the exponential side first, and then we'll come back to it later and do the log side. All right? So with 2.1, you just kind of fill in those two exponential function tables, which, again, if you didn't know how to do that, you could just put in Desmos, type the actual function, so like y equals 2 to the x power. You hit the here key, and then the little table that pops up next to the function, it'll generate the table of values for you. All right? You could have also did your TI, put it in y equals, type it in, and then hit second graph, generate the table that way. Now, go ahead and check your answers, at least for 2 to the x power. Now, just note that if you got, where'd it go? If you got this, if you got those decimals instead of the fractions, you're technically correct. Just make sure you note what the actual fractions are as well. Okay? So 0.125 is equivalent to 1/8. 0.25 is equivalent to 1/4. 0.5 is equivalent to 1/2. Just make sure you also have the fraction counterpart. So the purple graph over here, that's y equals 2 to the x power. Now, check for 1/2 of raised to the x power. And again, if you got these decimals, you are technically correct. Just make sure you also note the fraction counterparts. Now, the green graph that I have graphed up here is y equals 1/2 raised to the x power. So, before we talk about anything domain and range and all that stuff, let's go back to the front of your journal entry. So the side that says exponential function, so that front flap. So we talked about this on Friday when we did all those sample delta math problems together. All right. So today is kind of going to be a reiteration of things that we've already talked about on Friday. We're just actually going to be taking formal notes on it. Okay. So exponential functions. Remember, it's It's an exponential function if your variable is in the exponent. So the x is in the exponent. All right, that's why it's called exponential. Now, the standard form is f of x is equal to a times b of x. And sometimes you'll see it with the b in parentheses. It's the exact same thing. Now remember, we talked about this last week, but a is equal to the y-intercept, or the initial value, and b is your common ratio, or base, or whatever you want to call it. So remember when we talked about the common ratio, that was what number we were multiplying between all the different y's. Remember that from Friday? We don't have to get too in depth with that. We did most of that stuff back in Math 1. And honestly, in this class, most of it will be done justice anyway. Now, two types of exponential graphs you will see in this class specifically. This first one, we start low and then we get high. This is an increasing exponential. All right, so if we go from left to right, we start low and we got high. Now, this happens when your b value, so your base, is greater than 1. So any number that's greater than 1, could be 2, 3, 4.5, whatever. All right, as long as that base is greater than 1, you have an increasing exponential. Now, the other one is you start high and then you get low. That's your decreasing exponential. Now, that happens when your base or your b value is between 0 and 1. So what type of numbers are between 0 and 1? What do you guys think? What type of numbers typically? Decimals. So basically if it's 0 point something, has to start with 0. What's another name for that? Fractions. All right. So typically when you see that, I'm talking about a true blue definition of a fraction, meaning the numerator is smaller than the denominator. All right. So when you see this, we're talking about a fraction. So let me ask you this. Just to test. Three halves raised to the x power. Would that be increasing or decreasing? Increasing. Why is it increasing and not decreasing? Right. This is a fraction, but since the numerator bigger than the denominator, it's greater than 1. Okay? Now, if I had this would be decreasing because it's a true blue fraction, meaning the numerator smaller than that denominator. All right? It's a true piece of a whole. Now, both of these have what we call an asymptote. All right. What that means is it's a invisible line on the graph that your graph or the function itself will never cross. It will get infinitesimally close to it, but it'll never actually cross it. All right. So there's one here and there's one here. Now, how did I know where that asymptote was? It's when in doubt, it's at y equals 0. So exponential functions in particular have a horizontal asymptote, meaning it's a horizontal line located at some number. So you'll typically write it as y is equal to some number that your graph will never cross. So for example, again, asymptote just means a line your graph never crosses. It can be a vertical line. It can be a horizontal line. It can be a slanted line. However, we don't do slanted lines in this class. You'll only see asymptotes either vertical or horizontal. All right. Now, a lot of times it's really, really easy to kind of gauge where that asymptote is. For example, and you guys don't need to do this, but let's say I open Desmos real quick. All right, let's just say I did 2 raised to the x power like y'all did. Now, if you look, it looks like the line is like right on top of 0. But watch what happens when I zoom in like a lot. You guys see what's going on there? So this dark line right here, that's the x-axis. The red lines are graph. Even though it looks like it's right on top of the x-axis, it's not. It is so very like it's minute difference between the two, but it will never actually cross over 0. All right, so that's what an asymptote means. It gets super duper close to that line. It looks like it's touching it, but it never actually does. All right, it's almost like you guys know that Lilo and Stitch meme where it's like, she's touching me, I'm not touching you. It's like that. All right, you know what I'm talking about? Yeah. So that's what an asymptote is. It's just simply a line that your graph never crosses. Now, back to the 2 graphs that we already made up. Both of these will have a horizontal asymptote at y equals 0. All right, so a lot of times we draw our asymptotes as a dotted line, just so we know that's technically not part of the graph, but it's important to know where our graph kind of ends up. So this is our horizontal asymptote at y equals 0. That's our horizontal asymptote. And again, we could tell that just from looking at the Desmos graph. It looks like it's like sitting on top of the x-axis, but it's actually not. All right. Now let's talk domain and range. So remember, domain is what values? X or Y? X's. So I'm looking from left to right. We're only looking at the x-axis. So pay attention to what the graph ends in. So I'm looking at a graph of 2x first. Not 2x, 2 raised to the x power. What do you think my lowest x value is going to be for this function? So for this function, what's the farthest left value this function will have? It's an arrow. So that means it goes to negative infinity. It goes to the left forever. So we would start the domain by writing parentheses negative infinity. And remember, whenever you're dealing with infinity, you always use parentheses. Now, I keep sliding to the right. So this is my far right. What do you think my highest x value would be? Look at what it ends with. Positive infinity. Why did you say positive infinity? Because it's an arrow. If you guys see arrows, that means it keeps going on forever and ever in whatever direction specified. All right. So our domain's from negative infinity to positive infinity. What's another way I could state that? So I'm saying any number between negative infinity and positive infinity, I will have graph. What's another way I can state that? I kind of just told it to you guys. All blank numbers. All real numbers. So we could also say all real numbers, or the shorthand for it is the capital R with a line through it. All right. So if you said either one of these, that's totally acceptable. But just know that if you see that, it does mean all real numbers. Now, range. We're talking Y values now. Now, think about this carefully. What do you think your lowest Y value would be? Now remember, even though it doesn't cross that line, we still have a way to denote that it gets really, really close to it, but it never actually hits it. So, what do you think my lowest Y value would be? 0. Now, what notation would I use? Would I use a bracket or a parenthesis? So technically, 0 is where our horizontal asymptote is, meaning it won't ever cross it. So is it defined there or undefined there? What? Not a bracket. We use a parenthesis. So the reason we use a parenthesis instead of a bracket is horizontal asymptote, again, means that our graph never crosses it. That's another name for it's never defined at it. So even though it's infinitesimally close to 0, it'll never actually cross it. So we use a parenthesis to denote that it gets so close we can almost touch it, but it never actually touches. All right. So remember, parentheses mean undefined, whereas bracket means it's actually defined there. It smacks it upside the head. All right. It makes contact. But in this case, not quite. Now, if I go up, what do you think my highest Y value would be? Infinity. Because again, we got that arrow. So it keeps going up forever and ever. All right, so that was with Y equals 2 to the X power. What about Y equals 1/2 X? What do you think? What do you think the domain would be? All real numbers, good. So we have 2 arrows on both sides. So that means left to right, all the numbers are spanned. All right. So domain goes from negative infinity to positive infinity, or we could say all real numbers. Now, what about the range? So the range for the green graph. What do you think? It would. It definitely would. So it would start at 0, and it would go all the way to infinity. And with 0, we would still use a parenthesis because it's not crossing that asymptote. All right. Now, what do you notice about those two domains and ranges? So between the two tables or the two graphs, what do you notice about those two domains and ranges? They're the same thing. Two different graphs, same domain and range. The only difference between those two tables is that one of them is an increasing function, the other one's a decreasing function. All right, and we can tell that because, for example, 1/2 X, first off, the B value is between 0 and 1. Second off, if you look at the Y values, they're getting smaller as the X values are getting bigger. If you look at 2 to the X power, first off, B value is greater than 1, and the Y's get bigger as the X values get bigger. All right. Now, for domain and range with exponential functions, here's a little kind of cheat sheets. So, your domain, so for any exponential function, your domain will always be all real numbers. So your domain for any exponential function will always be all real numbers. The range, there's two different types of ranges you can get. The first one is the horizontal asymptote. So whatever number the horizontal asymptote is at to infinity. And that happens when your graph is above the horizontal asymptote. So it can look either like this or this. So if your graph is above the horizontal asymptote, all right, you'll go from whatever number the horizontal asymptote is to infinity, and both sides have parentheses. Now, the other way you'll see it is from negative infinity to your horizontal asymptote. And that only happens if your graph is below the asymptote. So if it looks like this or this, which it does happen with exponentials, all right, so it's below the asymptote, which again, that's the asymptote, you would get that type of domain. All right, so that's kind of your cheat sheet for finding range of domain for exponential functions. Yes, sir. We're about to take our break. All right, any questions on this? Okay, so here's what we're going to do. We're going to take our 5-minute breaks. I'm not going to set a timer, but I want you back in this room by 12:15. All right. When we come back, we're going to do your other journal entries, which is that sheet I had you grab at the beginning of class. All right. So go ahead and take a break. Be back in this room by 12:15. That's when I'm starting. So guys, have out the journal that you have to grab today. You want to go ahead and paste in your journal. It's just one that you fold in half. All right, so go after what we just did in your journal, but you just have to fold it in half. All right, guys. So new journal. 12:15. We're gonna get started again. So grab a new journal that you grabbed from the table today. If you want to go ahead and paste it in your journal, you just need to fold it in half. All right, and then paste it on the side where there's no writing. So it's an easy foldable. You just gotta fold it in half. All right, so we're going to put a pin in 2.1 and we'll come back to it when we get to logarithmic functions. So right now, I need you guys to completely shut your Chromebooks. All right, you don't really need them right now. Now, 2.2a is all about exponential growth and exponential decay. Now, we talked about this a little bit on Friday when we were doing those problems together, like I mentioned to you, the growth and decay formulas. All right. Now, today we're going to actually do the more formal notes on it and make sure you guys are pretty solid with this. I will say, if there's anything that you remember about exponential functions, especially when it comes to the EOC, this is it. All right. If you can remember these two formulas, you'll be okay in terms of exponential functions. All right. So I'm looking at the very front of that journal. So first off, we got exponential growth, which is given to us by this formula, A equals P times 1 plus R raised to the 2 power. Now, what these different variables mean is A is your accumulated value. Another name for that would just be your new value. So basically, after you do all your calculations, what do you end up with? Another way to think about it is typically growth problems. Think about, you got money in a savings account, it's gaining interest. That would be the amount of money you have in your account after, say, a year from what you started with. Okay. So, like, if you want a specific example, for example, let's say I had a savings account, had $500 in it, had 5% interest on it. So, after a year, the accumulated value would be the amount of money I have in my bank account then. All right. P is your principal. Now, that's just a fancy term in money for your initial value. So how much money did you initially put in? How much did you start with? What was the population that you started with? Things like that. R is your rate. So your interest rate, your rate of growth, your rate of decrease, whatever. That's typically given to you as a percent, but in here, it'll go in as a decimal. So you'd have to convert between a percent to a decimal. And then lastly, T is your time. And that's typically either in years, hours. Those are the two typical ones that you see it in, years or hours. depending on what you're talking about. All right. Now, that's growth. Decay is pretty much the exact same as growth, except for one key difference. So with decay, the only difference is that instead of adding the rate to 1, you're subtracting it. The variables mean exactly the same thing as it does for growth. So A is still the accumulated value, P is still the principal, R is still the rate, T is still the time. The only difference between the two is that one has a plus and one has a minus. The only difference. Now, a good way to remember which one is which is think about it this way. We know that the R has to be a decimal when we put it in. So the percent's now a decimal. What is 1 as a percent? So the decimal 1.0, what is that as a percent? It's 100%. So if you have 1, it's in a decimal form. Percent form is 100%. All right? So we're saying that we're taking our initial value and we're multiplying by 100% plus whatever the percent of our initial value is for the interest rate. So for example, let's say, again, at $500, 5%, let's say it accumulates once a year. All right, which that sucks, by the way, but you know. Anyway, so if I have 500%, that means I'd be adding the 500% plus the 5%, which 5% of 500 is. It's like 25. I can't remember off the top of my head, but anyway, it'd be like $20. All right. So then you would add that to the 500s after 1 year. That's your new amount of money. And you would accumulate that based on how many years. For 2 years, you would double that. 3 years, whatever. Okay? So that's a way to think about it. Now, decay is the opposite. So think about if you just bought a new car. Like, went to a dealership, bought a new car for, like, say, 30 grand. All right? That's how much you started with. Now, if you know anything about buying cars, as soon as you drive it off the lot, it starts depreciating and you start losing value. Meaning, if you brought it back less than a year later, they would pay you for the trade-in less than what you actually paid for it. All right. So let's say I bought the car and it depreciates 5% a year. All right, which that's really good, by the way. But that means that whatever our initial is, our new would be 100 minus whatever percent of our initial. So in other words, if this was 100 minus 5, you'd only be getting 95% of our initial value back after 1 year. All right, so that's another way to think about it. Now, one of these graphs here is growth and the other one is decay. So which one do you think is growth, the left or the right? The left. Why? It's increasing. It's growth. We are growing, so it's an increasing graph. And if you think about it, it does fit with what we said about the b value being greater than 1. Because if we're adding 1 to something, it's automatically going to be greater than 1. All right? So that means our other one is decay because it's decreasing. And it makes sense because our b value, which is the 1 minus r, we're subtracting something from 1. It's automatically going to be less than 1. Now, let's actually go through some problems and put what we just talked about to use. So, on the inside of that journal, go to the top left problem, the one that starts with Mr. Foster. All right, so Mr. Foster is starting a new job. His salary for the first year is $30,000. He'll receive a 5% raise each year after that. Write a formula to define Mr. Foster's salary as for the nth year. Clearly, Mr. Foster needs a new job because $30,000 is even less than what I can pay. I'm saying something. All right. So, what's some important information that I need? What's one piece of important information that I need? His salary after the first year is $30,000. So first year, $30,000. What else do I need to know? 5% raise each year. And then we're writing the salary S in terms of the nth year. Now, based off of the information given, do you guys think this is going to be a growth or a decay? Growth, because he's getting a raise each year, right? That means he's getting more money. So we're going to write exponential growth. So we're going to use the formula A equals P times 1 plus R to the T power. So before we do anything plugging in wise, we're going to go through and say what each one of those variables will be. So it's a very easy plug-in at the end. All right. So what do you think I'm going to replace A with in our formula? Not 30,000, because that's our initial. A is our new value after we do our calculation. So what variable specifically did it want us to say? S, because that's his salary after whatever year. So we're going to put S for A. What about P? So your principal or initial value. That would be your 30,000. That's what he started with. All right. So remember, P is your principal, which is another thing for your initial value. That's how much money they started with. What about R? So your rate. So it's 5%, but I need it as a decimal. How do I write 5% as a decimal? 0.05. Good. If you don't remember how to do that, just do 5 divided by 100 in your calculator. So 0.05. And again, it's because we wanted this as a decimal. Then lastly, what am I going to plug in for T, which is the time? What do they want us to replace it with? N, because it's talking about the nth year. That means instead of T, we're just going to write N. Now we got everything we need. So we're going to plug it back into the formula. So we're not going to do anything besides replacing the letters that we started with our new values. So this would be S is equal to 30,000 times 1 plus 0.05 all raised to the n power. So all I did was take all of these values that we just came up with and plug it back into their respective places up here. Now, I can do a little bit of extra simplifying, specifically right here. That's the only part of simplifying you need to do is just add or subtract those two values together. So what's 1 plus 0.05? 1.05. So our final one would be S is equal to 30,000 times 1.05 to the n power. So this is the formula that we came up with. So coming up with a formula isn't too bad. It's a matter of knowing which one to plug it into first off, so whether growth or decay, and then making sure you know which parts need to go where. All right, so now we can answer the next part of the question, which is after how much will Mr. Foster make after 7 years? So after 7 years, how much would Mr. Foster make? So, in other words, what do you think I want to plug 7 in for? N. So 7's just going to go in for N. So I have S is equal to 30,000 times 1.05 raised to the 7th power. And then there's no solving or anything crazy like that. All we got to do is just take this and put it in our calculator. All right, so take a minute, throw that into your calculator, and literally, if you just type it in as you see it, it will pop up. So 30,000 times 1.05 raised to the 7th power. Now, if we're talking money, what would be a reasonable place to round to? Not the tenths, the hundredths. So that's 2 decimal places. All right. So in other words, we'll cut it off right here. Okay. So if they don't tell you where to round to, pick what rounding that would make the most sense. So like if we're talking money, 2 decimal places. Right? Because you don't see $1 and 1.25 cents. That doesn't make sense. All right. So our answer would be after 7 years, he'll be making approximately $42,223.01. Whoopee, they gave you an extra cent. So that's how much you can make after 7 years. Maybe it's again his job. But now we're about where I'm getting paid now. Any questions on that one and how you would set it up? Yes, sir. It's 213, isn't it? Oh, Lord. That right? Okay. All right, let's try another one. So let's look at the next one down. So Janet purchased a new car for $25,000. The moment she drove the car off the lot, it began depreciating 15% per year. Write a formula to define the value of Janet's car V after N years. So first off, just based off the information that we have, do you guys think it's going to be a growth or a decay? Decay. Why? What word kind of clues you into that? Depreciating. So this is definitely going to be a decay. So we're going to use A is equal to P times 1 minus R to the T power. So some important information. The new car was $25,000. It was depreciating 15% per year. And we want the value of Janet's card V after N years. So we're going to do the exact same thing that we did for the previous one. We're going to write out what our different values are first before we put them in our formula. Now, guys, you don't have to do this necessarily every time, but this is a good way to kind of learn it first so you can actually see, okay, this goes here, this goes here, this goes here. It's just a good way to kind of organize it. All right, but once you get good at it, you can just, go straight into the formula. So, what do you think I'm going to plug in for A? So, it's our new value, so V. Because they want the value of Janet's car, V. Well, accumulated value is the new value of the car. What goes in for P, or our principal? 25,000. That's how much money she paid for the car. What's our rate as a decimal? 0.15. Good. So 0.15 is our rate. And then what am I plugging in for time? N. So she says after N years, so N. So if I take this and plug it back into my formula, I get V is equal 25,000 times 1 minus 0.15 raised to the n power. Once again, I'm going to simplify what I have right here. So just go ahead and do the subtraction just to save me some time. And that'll be 25,000 times 0.85 to the n power. So that means after every year, our car is only worth about 85% of what it was initially. So this will be our new formula. Any questions so far? Now, we now have enough information to answer the next question. So how much is Jan's car worth after 4 years? So where am I plugging in the 4 for? N. So we're going to plug 4 in for N. So this will be 25,000 times 0.85 raised to the 4th power. So someone put that in their calculator. Tell me what you get approximately. Round to the nearest cent. Say it one more time. So it's $13,050. How many cents? 15? Okay. Is that what y'all got? So when you guys put in your calculator, is that what you got? All right. So that would be correct. And remember, whenever we are rounding anything, make sure you put your approximate sign, so that little squiggle equal sign. It means that that's not the exact, but that's approximately what it is. All right. All right. So do me a favor and try the next one, so the top right one, on your own. So it's very similar to the first one that we did. Yes, sir. All right, so give that top right one a shot. Figure out whether it's growth or decay. There's at least one keyword in there to tell you which one's which. Does anyone have a charger I can use? My computer's about to die of work. All right. So you're just doing that top right one. All right, thumbs up if you're ready. I'll give 1 more minute. All right, so let's set up the function first. Now, I'm not going to write out what each letter should be. I just want you guys to tell me, just kind of going down the line. So first off, would this be a growth or decay? It's definitely a growth. Why? Right, the population's increasing. So keyword increased. All right, it's the growth. So we're dealing with A equals P times 1 plus R raised to the T power. So what did you plug in for your A value? Hit BY. So that's the population. All right. It really doesn't matter variable wise. Typically, you just want to keep it to what it's asking for. So Y equals, what was your initial? 6.09. Now, even though it's billion, you didn't have to like actually figure out what the billion part is. You just put 6.09, then whatever answer you get at the end, whatever answer you get at the end, you just write billion after it. That's all you have to do. All right. Now, times 1 plus, what was the decimal you got for the rate? Close. Missing something in there. 0.0118. So 0.0118. And then we would raise it to the n power. That's our t value. So if we simplify that a little more by adding y equals 6.09 times 1.0118 to the n power. Now, be careful about this next one. It says estimate the world population in 2005. Did you plug in 2005 for the n value? What would your n value be? 5. Why is it 5? Right. It says that this is our population in 2000, and every year after 2000 is what this increase is coming from. So, since 2005 is 5 years after 2000, so you could have just subtracted 2000 to 2005, got 5 years. This is what you plug in for n. All right, so sometimes you will get thrown a problem like that where it's like, okay, they started this year, what's it during this year? And you have to figure out how many years actually passed. Okay, so this will be 6.09 times 1.0118 raised to the 5th power. It's equal to y. And then what did you get approximately? Let's say 2 decimal places. So if you're out of 2 decimal places, what would you get approximately? So guys, it just goes in your calculator. 6.459. So let's say 6.46 billion people. All right. So even though we didn't have to convert this to billions, we still need to make sure that we say that it's a billion people. Because 6.46 people wouldn't make sense. Now, if this was on the test, I would not dock you if you didn't put your units. Just get into the habit of putting your units though, because it'll help you in the long run, especially if because the EOC can be evil and they switch units on you in a heartbeat. Like, oh, we started with feet, now I want it in yards or want it in inches or whatever. You know what I mean? Just get in the habit of getting those units down. All right, how are we feeling? All right, let's do this last one together, and then we'll be pretty much done for the day. All right, so yeah, is that what you need? So you take a 325 milligram ibuprofen. During each subsequent hour, the amount of medication in your bloodstream decreases by 29% each hour. And let's write the equation to show the amount in milligrams of ibuprofen in your bloodstream after T hours after the initial dose. So, the best way you can describe this, if you don't know medicine that well, this is the reason I shut the door. You guys know those old cop shows where they're trying to figure out how much a person may have taken of a certain drug, and see if they're still high. So they just, you know what I mean. So, anyway, basically, you have the initial. So you know, shoot some coke or something. It's fine. You have the initial, then it's in your bloodstream for so many hours. So every bloodstream, if you don't take any more within that couple of hours, it decreases. All right, to the point that your blood fully absorbs it and it's out of your system. All right. Same thing if you ever took a pain med, it only lasts for like 6 hours or something, and then it's out of your system. That's what we're trying to figure out now, like how much is in your system after so many hours. All right. Just so you guys know, I can get fairly off color sometimes with stuff like this because I want you guys to remember it. And sometimes, talking about doing drugs is the way to get you guys to remember this. Okay. So, trust me, wait till you get to rational functions. It gets interesting. All right, so that one. All right. So, do you guys think this could be a growth or decay? Definitely decay. We're looking at how much is left in your bloodstream after so many hours because it's going away slowly. So, Y is my A value. What would be my initial? 325. Good. So that's the amount of the dose that I took. And since it's a decay, we're doing a 1 minus. What's my rate of decrease? So what's the rate that I'm decaying? It's 29%, but what is it as a decimal? 0.29. So 0.29, and it's going to be raised to the T power. So if we simplify that down, it's y equals 325 times 0.71 to the T power. Now, we want to know how much is left in our bloodstream after 3 hours. So I'm going to plug that in for N. So y is equal to 325 times 0.71 cubed. So someone put that in their calculator. Tell me what you get. Let's say round to 2 decimal places. 697. Double check it because it should be smaller than the initial. So guys, that's actually a good lesson in how to know if you may have made a mistake If we know it's a decay, it should be smaller than our initial. Right? So if it's a growth, it should be bigger than our initial. Yep. 116.32? Okay. 116.32 milligrams. All right. Any questions on this? All right, so make sure that that's pasted in your journal. It's going to go after the one that we just did today, earlier. Now, there is technically a delta math for 2.2. It's already assigned to you, but we're technically not done with 2.2. We still got 2 more parts to do. So you may be able to do a little bit of it, but if it's something that you definitely know that we have not covered yet, don't worry about it yet. I pushed the due date off for a little bit. Now, for the rest of class, what you can do is your optional assignment, which is pages 1 through 4 of your new packet. All right, it's just on the stuff that we've done today. So plugging it in, putting it in your calculator, getting an answer. All right. So you guys got a solid 15 minutes, so use your time wisely. That's what I recommend you do. So guys, everyone has their packets out. Work on that. Okay, test corrections. So I'm finishing up the box today. Essentially, I can give you like the kind of rundown on how they work. So essentially, if you want to do test corrections, you typically either have to do them in class in your classwork time or after school, because I can't allow you guys to do tests at home. Just for security reasons if you do reuse tests. I will take test corrections up until the end of the term, and I don't have exact instructions on how that works, right? But as soon as I'm finishing that up today, and then I'll tell you guys more to go. But essentially at any time. It's where? Go to the unit key page. So if you're on my homepage, hit unit keys.